right, so today we're going to look at graphing polynomial functions. And we're talking high degree functions to the 10th, to the 12th, crazy functions. It's going to be fun. Here we go. Ideally, you could graph these first ones without much trouble. You should know what a parent graph of a parabola is, or of a quadratic. It's just going to graph as this parabola shape. And ideally, you know that a cubic is this like little snaky thing that swoops up and looks like this. All right, but how about higher degrees, fourth degree, fifth degree? All right, well, if I'm doing the tutorial here, so I guess I'm going to save you from typing it in your calculator, but a quartic actually looks like a quadratic again. The only thing that changes is a little steeper on the sides and a little flatter across the bottom. And a higher degree, like a fifth degree, looks sort of like a cubic, but it's a little straighter because it's increasing much more quickly, so there's not as much curve going on. Probably more than what I just did there, but all right. So then if you keep jumping higher degrees, an eighth degree, same deal. It's going to be really steep, it's going to be flat, and then it's going to come up. But a ninth degree is, again, looks like the cubic. Now, I'm just kind of going through this and I'm not commenting. Do you know when is the difference between when it's going to look like that parabola and when it's going to look like the cubic? Any guesses? All right, hopefully you're catching on that, oh, on the evens, it's going to look like a parabola. And when I say the even, I'm talking about the power. And if it has an odd power, it's going to have that cubic look to it. So that's the trick. If n, which is the power, is odd, then the n behavior looks like, oops, sorry, if it's odd, looks like this. That's a little extreme. And if it's even, it looks like a parabola. But really, we're talking about the end behavior as what's happening at the ends. So you can see that on a cubic looking one, all of these, it starts down low and it ends up high. So if you think of that on a graph like this, and you have some graph that does this. All right, so as x is approaching negative infinity, your y is also approaching negative infinity. But if x is approaching positive infinity, then your y approaches positive infinity. So let's fill that in. As x approaches infinity, so does y. As x approaches negative infinity, so does y. All right, let's look at the even powered ones and how those would play out. So I'm going to sneak this in over here. When you have a parabola looking shape, as your x approaches, let's go to infinity first here. As x approaches infinity, your y approaches infinity. As your x approaches negative infinity, oh, this is different. It's the y is still going up. So the y would approach infinity as well. So in both scenarios, the y is approaching infinity. All right, so it's time to get a little fancier. I'm going to look at some functions, and I want you to imagine that this polynomial is all multiplied out. And so it'd be like some kind of big, long polynomial with an x to the fifth times an x to, or I'm sorry, an x to the fifth plus an x to the fourth plus an x to the third and so forth all the way down. Except that what I'm going to do is I'm going to give it to you like it was factored out. So in this case, it would have been a quadratic, but I've factored it out for us. Now, we should know that when you factor it and you set those equal to 0, you find your x-intercepts. So I end up with an x-intercept. A fancy word for that is called a zero. The zeros are at 3 and 5. So I've plotted them right here at 3 and 5. Now, because it was a quadratic, if I were to have multiplied that out, it would have ended up an x squared something. That's what the end behavior will behave like. So it looks like a parabola. It's going to start high, it's going to end high because it has that even powered behavior. Now, at this point, I mean, even though I didn't make you do the graphing on your graphing calculator anyway, but we are not using a graphing calculator. You're going to find that you get crazy numbers and they really don't graph nicely on your calculator. So much so I have not even put on a scale. I've put some tick marks, but you have no idea what they represent. They might be every 1, they might be every 100, every 1,000,000. It doesn't matter. We're not going to pay attention to anything vertical. We're just more looking at what's going on horizontally. Let's try a few more. This next one, you can see that it would end up being a cubic because it's an x times an x times an x. So my end behavior is going to look like a y equals x cubed, which in my mind means, oh, it's going to start low and end high. But it has 3 different 0 values. I'm going to have a 0 at 2 and at 5 and at 6. So what's going to happen is, yes, my end behavior starts low and ends high, but I've got other stuff going on in there. So this is going to start low. It's going to come up here and cross at 2, and then it's going to cross at 5, and then it's going to cross at 6. And then it ends high like I know an odd-powered polynomial would do. Okay, let's try a few more of those. In this next one, this one's different because I put a 1/2 here. Now that 1/2 would do the same thing that a value does on all of our other functions. It's going to be a vertical shrink. However, remember I said I don't care about anything vertically. So yes, it's there, but it's not going to affect how I graph it. I'm going to have these 3 zeros. So it's at -1 and at +2 and at +4. Since there's 3 x's in there, it's going to behave like a cubic. It's going to do this. So I want to start low, come up and cross at all of the 0 marks, and it should end high, like that. Okay, you try this next one. Go ahead and pause the video. Right, here's what I've got. I ended up with 5 x's on this one, but that's another odd. I should have thrown an even in there to do that, but all of these end up with odds, so they all start low, end high, and just zigzag through there. It's kind of fun to draw. Okay, let's throw another kink in it. So we're going to graph polynomials that have multiplicity. And by multiplicity, we mean that something occurs more than once. So if you'll recall, the graph of a y equals x squared, it had that parabola look to it. But what I'm doing here actually, well, let's go ahead and do, in the cubic did this kind of a thing. What I'm specifically looking at is what happens at x equals 0. On all of my even powers, it turns around. And so what we say is that it kind of like hits and goes back up. So we say it bounces at that spot. But if you had an odd power, it just goes right on through. And so we say that it cuts through. So on even powers, we'll have this bounce look to it. Odd powers will have a cut look. So if they want us to do this, we should know, oh, that's an even power, so it's going to start high, it's going to end up bouncing, and then it's going to end high. On a 5th degree, it's going to start low, it's going to cut, and then end high. Now let's do it with something more than just having it the 0 at 0. Oh, I did put this at the top of the next page so that you had a play. I didn't want to kind of give it away what we were looking for there, but I'm giving it away in the video anyway. So when does it bounce? It should bounce on even powers. When does it cut? On odd powers. All right, so let's look at a few. This next one, again, still not using a graphing calculator. When I look at this, your end behavior is actually, it looks like there's 2 zeros here, but it's actually 3 x values because the second one is squared. So it's like an x times an x squared. So our end behavior is going to actually be an x cubed, y equals x cubed. So that means it's going to start low and end high. But I only have 2 zeros. I have a 0 at 1 and I have a 0 at 2. But because the power on the x minus 1, that's assumed to be a 1 and it's an odd, then it's going to cut there. But the x minus 2, that is creating a 0 at 2, it has an even power, so it's going to bounce at that spot. So starts low, cuts at 1, comes around, and it's going to bounce at 2 like that. So it just touches at 2 and then keeps on going. Now, these are all very curvy. When I say bounce, I don't mean like a ball and it's pointy. Not like that. Don't do that. It's nice and curvy. All right, let's try this next one. This one's going to behave like an y equals x to the 5th because you have 2 here, plus you got 3 more there. So you got a total of 5 x's laid out here. So that's going to look like a y equals x to the 5th. Start low, end high. It only has 2 zeros at -1 and at 2. And since this one at -1 has an even power, it's going to bounce at that spot. But the 2 has an odd power, so it's going to cut at 2. Let's see what that will look like. A 0 at -1 and at 2. I'm going to start low. It's going to bounce here, so it just hits, but it's going to cut here and go on up, so it ends high like I know it should. How you doing? Making sense? All right, we're going to make them a little bit harder and add a little bit more of what you have to do. Okay, so on this one, I'm going to count up my x's. So I've got 2 here, 1 more, 3 more, 1 more. So ultimately, you're just counting exponents. So there's 2 plus 1 more, that's 3, plus 3 more, that's 6, plus another one, that's a 7. So that's where we're getting this in behavior of y equals x to the 7th. If there's no power, we assume it's to be a 1. When you look through the different options here, you're going to have 4 different zeros at all of these spots. Which ones do you think it will bounce out, and which ones do you think it will cut at? Since it bounces at even powers, it should bounce at the -4, and that's it. Because the others are all odd powers, so it's going to cut at -2, at 2, and at 5. So let's put x-intercepts on our graph at those spots. Now, I have a tendency to, because we're going to end up with more. This is only 4. I told you we're going to get 12. So I tend to start labeling them as I go. This is going to be a bounce, so I'm going to put a tiny little b under here so that I don't have to keep peeking back up to see what it does. Once I get these in, I just want to flow through and draw my graph. These are all little cuts, so I put a little C there. Now, it's again an odd. I must like the odds. It's going to start low, end high. All right, so that means I come over here. First one's a bounce, nice and curvy bounce. Then it cuts, 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 and there I am ending high. If it doesn't end like you know it's supposed to, then you probably did something wrong with your bouncing and cutting, and you'd go back and look. It kind of checks itself a lot of the time. All right, so I have another one. Now I'm going to add in this box over here on the right that I want you to start filling in. This one I've partially filled in for you. The end behavior is a y equals x to the 10th. Let's see if we can see where that's coming from. So you have 2, that's a total of 5, total of 9, there's your total of 10. So that's where the x to the 10th is coming from, adding up the exponents. Because it's an x to the 10th, I know that the end behavior is going to have this parabola look to it. Well, it doesn't really look like a parabola because there's so much going on, but the end behaviors are both upward. So this is the next thing I'm going to have you fill in. As x approaches infinity, y will approach infinity. So you don't have to sketch this. This is kind of telling me that. If x goes towards negative infinity, my y is still headed up towards positive infinity. Now, let's list which places, which zeros we think it will bounce at and which it will cut at. Bounces are going to happen at all your even powers. So that's going to happen right here. That has a 0 of 2. And it's going to happen right here. That has a 0 of 5. So it's going to bounce at 2 and 5. And then it's going to cut at the other ones because those are odd powers, so at 3 and at 6. So I'm going to go ahead and plot those. 2 and 5 are both bounces. 3 and 6 are both cuts. Now, the other thing I want to check is my y-intercept. So to check the y-intercept, you have to put 0 in for x. You're going to put 0 in for a lot of x's. You're going to put a 0 in right here. When you put 0 here, you subtract 2, that's -2. Squared is 4. Times, because these are all being multiplied in here, the next factor, when you put in a 0, is going to be -3 cubed. So that's a -27. Times, put 0 in the next one, and you get a -5 to the 4th power. Anybody? You know that one? -5 to the 4th. It's going to end up positive 625. Times, and then plug 0 in for x here, and you just get a -6. So now what you're going to do is multiply those all together. Now, I unfortunately did not have my calculator handy here, so I'm going to make you multiply those, and you're going to fill in right here what that y-intercept is. I'll give you a moment to do that. Well, maybe just pause the video, go do that. Okay, now I'm not going to tell you what it is because I didn't go get my calculator. Let's just keep moving. I do know, though, that it's going to end up a really big number, but it's also going to end up a big positive number because I've got 2 negatives there. So what that means to me is that my graph should have a y-intercept somewhere up here. Again, it's not scaled, doesn't really matter, but keep track of that. It's really going to end up pretty high. Okay, now I'm ready to sketch a graph. It's supposed to have ends that both end up upward. So here's my graph. I come through here. First one is a bounce, and then a cut, and then a bounce, and then a cut. And there it is, ending upward like I wanted it to. Good deal. All right, so now I'm making you fill out more of the box on your own. It says, for each problem, describe the end behavior, place a tiny b or c on each of the zeros, find the y-intercept, and again, you plug 0 in for x to find that, and then you're going to graph it. So the first thing we want to know is our end behavior. So we count up the x's. So here's an x, here's 3 more, so that's a 4 total, 6 total, 10 total. All right, I got another y equals x to the 10th is my end behavior. In my mind, that means it starts high, ends high. Bunch of other stuff in here, I realize that, but it's going to start high, end high, which means that as x goes to infinity, so does y. If x goes to negative infinity, y still headed up to positive infinity. Next thing they wanted were the zeros, the bouncing and cutting. So I'm going to have a 0 at 2, and it's to the 1st power, so that's a cut. 0 at 3, odd power, cut. At 5, even power, bounce. 6, even power, bounce. Now, I got to find my y-intercept. I still don't have my calculator, but I'm going to walk you through it. You plug 0 in for x, and you get a -2. Now, this 7, I told you that it doesn't matter. It is not, we ignore it and stuff. Well, it does have a vertical stretch, and it will affect my y-intercept. So I do include it as I'm multiplying these numbers together to find the y-intercept. I just don't worry about the vertical stretch as I graph. Next one, 0 in for x, I get a -3 cubed. That's a -27. 0, -5 squared. Oops, don't think I know that one off the top of my head, so I'll let you finish that up, and you're going to find this. I guess for me, for what I'm going to do right now, I just want to know, is it positive or is it going to be negative? This is going to end up positive because it's to the even power. So it looks like I have a negative times a negative. I'm going to end up with a positive y-intercept somewhere here. All right, let's graph it and let's see if it does what we're supposed to. It's supposed to start high. So I come up here, and the first thing I'm going to do is I'm going to cut through, bounce, bounce, and back up. Again, if it doesn't end like you know that it's supposed to end, then you probably goofed up and go check. See, did you bounce when you were supposed to cut or something like that? Or maybe you got your y-intercept wrong and had it down here, and then that didn't feel right. So check those things. Okay, we're close to done. Let's go do just a couple more. Sorry, I lied. I was thinking, gosh, I got a couple more of these. I feel like we got it figured out. We haven't figured out. You're supposed to go finish the rest of that, all those graphs. Now, on the very back page is kind of an application problem for these polynomial functions. So I'm going to go ahead and go through this. So it's a problem. It's a classic calculus problem in all honesty, but we're not going to get that deep into it. It's the volume of an open-topped box. And you missed out with my fun, cute little video of my kids when they were little, and I made them make a video. But here you are. You get to see they made a box out of a piece of paper. And it sort of was like this diagram here, where they cut corners out of that piece of paper. And when they cut the corners out, ultimately what they were able to do is like fold this piece up and fold this up and fold this up and fold this up and tape it up. And it's a box, just there's no lid to it, there's no top. So it's an open topped box. Now, what they did is I was offering them M&Ms, and if they built this box, I'd fill their box up with M&Ms. And so they all kind of like, I have 3 boys that were in it, and they were all like making different sizes of squares. And I was like, well, does that even matter? Would it still hold the same number of M&Ms? And so I guess right now I would ask you, if you take this square and you cut it out and you build a box, if this square was really tiny, then you'd sort of have a really low, a big base on it, but it would be kind of low, wouldn't have much height. And as this square got bigger, your base would start to get smaller, but then the thing gets taller. So right now, then I guess I'm wondering, do you think they would all have the same? Or do you think the volume would start to get larger? Or do you feel like the volume would start to get smaller as you started to make this bigger and bigger? Think about that. Maybe jot it down. Let's go check. All right, so here's what we've got. We've got a piece of paper. It's a 9 by 12 piece of paper. And we're trying to ultimately maximize the volume because we want to get the most M&Ms, obviously. So if you look at your piece of paper down here, it was a 9 by 12 piece of paper originally. But then we cut these corners out. If I cut this corner out and cut this corner out, and then I tip up that edge, and I'm going to do that all the way around, this becomes the base of my box. And it is no longer a 9 by 12 base. The paper was 9 by 12. But what would this new measurement right here be, do you think? And I guess I need to know this measurement as well. Well, the whole length used to be 12, but you subtracted out 2 side lengths. We don't know what size they were, so we're calling them X. But since you cut it out of both sides, that new length is going to be 12 minus 2x. What do you suppose this length is going to be then? Of course, 9 minus 2x. Okay, so with that concept, we're going to write a volume function for what the volume of that box is going to be. So remember from whatever, pre-algebra or geometry or whatever, the volume of a box is length times width times height. So the length looks like we have a 12 minus 2x. And our width is a 9 minus 2x. And what do you think the height of the box would be? Well, if you fold up that flap, it's actually going to be the height of that flap, the X that you cut out. That's how tall your box will end up being. All right, so now there's our polynomial function right there. let's look at it and see if we could graph it. It's going to behave like a y equals x cubed. Okay, got it. Start low, end high. And it's going to have a 0 at, if you set this equal to 0, you can probably do that in your head. You'd have a 0 at 6. If you can't do it in your head, then you set it equal to 0 and go solve. Subtract the 12, so divide by -2. If you do it on this one, it doesn't come out quite as nice. You're going to subtract the 9 and divide by -2. Not bad. We could do that. And then we also are going to have an x equals 0. So over here, these are all to the first power. So they are all going to end up cuts. It's going to start low, end high. It's going to look like this. All right, let's keep moving. All right, so let's talk about what's really going on and what this graph is representing. First of all, it says, do you really need the full graph? Box in the part of the graph that you really need to look at. So there's a couple things. I think before I even do that, I'm going to go through these questions here. What do the x values represent? Well, when you think of what your function was, what did we make x equal? Okay, we had that equal the size of square that we cut out. And then I'm going to jump down to this line where it says, what does your y value represent? So your y value is your y equals your whole function, but our y was really volume. It was a volume function. So the y value is representing volume. Now, when we're looking at trying to decide what makes sense, does this part make sense for size of square or for volume? No, you can't have a negative size of square. You can't have a negative volume. I don't want this, but this should be okay. They're both positive. That's good. That's good. But right here, I'm concerned about this chunk right here. This would represent a negative volume. The x value is still positive, so I'd have a positive size of square, but I can't have negative volume. That doesn't make sense. And so that's not going to work. And then maybe this still works. Let's talk about what's going on your piece of paper. Let's say this was the piece of paper. And then when you cut the corners out of this, it was 12. So when you look at the 6, remember the 6 was the 0 that came from that? Would it make any sense to let this square get bigger than 6? Because here you are. You end up with a square of size 6. These are going to end up merging, and you're not going to have any flaps at all. So that's why this becomes problematic. And it works the same way here. Think about that 9. You can't go any bigger than 4.5 on either side because it merges. So really, I don't even care about the 12. I can't even make these squares 4.5. And that happens right here. If you start to make those squares bigger than 4.5, you can't even get a box built anymore. So this is where that starts happening, being problematic. And I don't even care about this because it would never work for the rest of it. So the only piece of this function, so I'm going back to this, what do I really need? Box it in. I only need this chunk right here. That's the part I can use. So let's go ahead and box that in. This is the part of the graph I want right there. I'm ignoring all the rest. Don't care. Don't care. All right. So let's look at this. What values do you really need? What makes sense? What's x values? I'm back to the top. What x values do you really need? So when you look at this for the box, what are our x values? Well, it goes from 0 to 4.5. That's our domain. When you're looking at x values, we often think like, why do I need to know the domain? Right here, this is why the domain is important. You can't let that x value get any bigger than what's allowed for the paper. So do you think it could actually equal 0 or actually equal 4.5? Well, I'm going to say no on 0 because you wouldn't even have a box. So I'm going to do a parenthesis. But what would happen at 4.5? If you let it be 4.5, you still are not going to have a flap to build up. So I'm going to do a parenthesis on both. Can't be either of those. Now your range is how low it goes and how high it goes. So now I'm looking at the lowest, and again, I'm looking at the box, is right here. It doesn't ever graph down here. It starts right here. The lowest it gets is 0, and right there is the highest it gets. I don't know that value yet. So the lowest would be 0, still can't be that. And the highest is, how am I going to find that number? I hope you're thinking, hey, I should grab my graphing calculator out, and I could do it that way. All right, so that's what we're going to do on this. Now, I still don't have my graphing calculator, so you have to do some of the work here today. Was your boxed area correct? Well, yeah, I kind of forced us into making the boxed area correct. And so we can adjust our window, which means on our graphing calculator, and sketch the new graph. All right, so here's what I want you to do. At this point, I want you to type into y equals the volume function that we came up with, get an appropriate window where you can find this, and you're going to need to find this maximum value right here so that you can finish out the range. And then this is a circle on your graph, the point that helps you determine how to maximize the volume. Well, the maximum volume is the highest, and it's going to happen right there. That's where I want you to circle, that maximum. And then I know that you know how to find the maximum on a graph, right? Go to that second trace, go to that calc menu, and you'll find the maximum. And then you can kind of finish this out. Now I'm going to want a sentence on this. So I want to know in general, like, what does that X and Y value mean in real world sense? Write me a nice sentence. Okay, I have one other thing that I do want to talk about. I want to go back to the question of, does it even matter how big the square is? Is the volume the same always? And the answer to that is, yeah, it does matter. If you make a really small X value, a small square, your volume isn't actually very big. And the bigger you make the square, the bigger your volume gets, to a point. And at some point, when you start making it really big, it gets to be a really tall box, but it's such a small base that the volume starts to decrease again. So there's like this happy medium here. Now on your calculator, you can probably see that it's not all necessarily symmetrical. So don't think it just always falls in the middle. That wouldn't always be the case. So go ahead and use your calculator to find those numbers that you need and to write me a nice sentence here. Okay, I'm done. Thanks for joining. Talk to you later.